amazing benefits. I mean, the most amazing benefit of fusion is that it kind of mitigates energy, food, and water scarcity for humanity. What could we do if energy was ridiculously cheap?
Abundance.
Abundance.
Everywhere.
Yes. We would have the ability to desalinate the ocean in order to provide fresh water. Nitrogen for fertilizer is created through electricity. So all of these things suddenly come and solve great, huge problems with fusion. Fusion occurs when two light atoms, deuterium and tritium, bond together to fuse to make heavier atoms. It's really kind of simple in theory. It's kind of hard in practice. But as we'll talk about, it's a remarkable thing to be able to generate enough plasma, which is kind of a small sun, tiny little sun, at 100 to 150 million degrees Celsius, which we can do now, and then transfer that energy to a heat exchanger, which then extracts the electricity. And fusion is kind of real, right? Our sun runs on fusion. But at Lawrence Livermore, just this about 18 months ago, we achieved Q greater than 1. That means we are generating more energy out than energy in. Right? That's really freaking cool, right? And so by doing this, it allows us to envision a future with a little seawater, because that's what deuterium is mostly made of seawater, and tritium, a byproduct of nuclear fission, if you will. We can take wasted materials from nuclear fission, reuse it, and have really clean, really abundant, perpetual energy. Sound cool so far? The challenge is we've done this in a lab, but now bringing this to commercial fruition is kind of, right now, science fiction. If you can envision putting a small sun in a reactor and then finding a way to capture its energy through heat that then gets pushed out to water that then turned into steam that just generates a turbine that generates electricity, right? How do you build something that can withstand that much radiation and heat that you can then capture that commercially, efficiently, effectively? And so right now, most fusion reactor infrastructure is theoretical. The heat transfer aspects in those materials, that first wall, are being developed but aren't here yet. They're really science fiction. And we've got some other challenges as well, but I want to focus on the first wall because it's the next big challenge. And so what we need to do is together we need to build a cyclotron, an industrial cyclotron. A cyclotron is a linear accelerator that generates atoms through in a very quick fashion and smashes against something. And the reason we want to smash it against something is we want to determine what its reaction will be when it's smashed against. Because when we put this small sun in a first wall environment, there's going to be a lot of smashing going on. Radiation in forms of gamma rays, X-rays, neutrons, protons, heavy ions, and the like. And there are existing nuclear fission locations that can do most of that nuclear hardening testing. But what we can't do is test for heavy ions and protons, and the only way to do that is through a product called a cyclotron. Radiation testing, though, is necessary and difficult. It's mostly difficult because there aren't a lot of facilities. Most of the facilities were made for the Manhattan Project in the 40s, 50s, 60s, and 70s as we were building out this nuclear arsenal. But a lot of those facilities have faded away. Today, if you don't count the medical cyclotrons, just the industrial cyclotrons, there are only 11 in the US. And the average wait time to get 1 hour of use of a cyclotron is 36 months. So if you want to go build something, we're builders here, in that first wall environment, you got a 36-month wait before you get to try it once. This is the rad testing process at Stanford. There's a cyclotron at Stanford. And as you can see, this is a 36-month process from start to actual testing. The second time you want to test, it's only a 24-month wait. But envision being iterative and trying to want to test quite often. Quite the challenge. So cyclotrons aren't just good for materials, they're also good for electronic componentry, because we need electronic componentry in these systems to measure what's going on in there, right? And those are the same electronic componentries, those integrated circuits and those sensors that are getting bombarded by radiation, and we've got to figure out whether or not they're going to survive or not. The material side of this is really complex. But one of the side notes of cyclotrons is it can also produce tritium, which is what currently is being priced at $30,000. I said you needed tritium and you needed deuterium in order to bring those two atoms together. So cyclotrons can actually create tritium, but they can also test that first wall. So there's a lot of ways to make money with cyclotrons. They're especially necessary for fusion reactions. And I've always looked at fusion as this 10 to 20 year solve problem kind of timeline, right? 10 to 20 years away from now. But in order to do that, we need to take this science fiction, this infrastructure around a fusion generator, and make it real. And the way that we're going to do that is through a cyclotron. Cyclotrons aren't easy. They require enormous amounts of energy, so you need to be putting it next to a power plant. It requires, lots of PhDs, probably 10 to 15 PhDs that are nuclear physicists to kind of run these things. To build them requires an enormous amount of infrastructure support, project management, a little bit of customization, because you just don't go to Amazon and say, I'd like to buy a cyclotron, right? These are $100 million kind of endeavors. The dimensions of a cyclotron are sort of in the 300 by 300 square meter kind of environment, right? And then you have all these regulatory and safety considerations. But the good news is, unlike nuclear fission, which requires years and years and years of regulatory behavior, a fusion environment or a cyclotron environment has about the same regulatory hurdles as a hospital. In fact, most hospitals, including the one here in Santa Cruz, have cyclotrons in them, just cyclotrons that are pretty small, don't create heavy ions, and don't create protons. But they're used to create radioisotopes to treat cancer. So they're kind of important. So cyclotrons aren't easy. But I will tell you that when you create a cyclotron today, the cyclotron at Stanford is generating about $50 million a year, running 24/7, 365 days a year. It generates that revenue at about somewhere between $100,000 and $200,000 a beam hour, And in a cyclotron, you can have somewhere in the neighborhood of 12 different chambers in which you create targets so that you can test 12 different targets at the same time. So lots of opportunity for revenue. It's going to require $100 to $120 million in investment, but most of that will probably come from vendor financing, right? Because these vendors see a hard asset that they can use. The ongoing cost to employ these PhDs is about $6 million a year. So this solves a really big problem. We think there's a nice plot of land that UCSC owns down in Marina, right next to Joby, that could fit this bill quite well. One of the vendors has already committed $25 million in financing. And we just as a community need to decide if we want to be the ones that go and build this. So my ask is, do we want to go build the nation's next cyclotron? Thank you.